strings P and Q are identical, and string P is under greater tension than Q. Figures show three situations in which standing waves exist on two strings. Which of the above strings could represent the strings vibrating at the same frequency? They have given that there is the same frequency, but tension of P is greater than tension of Q. I will consider P and Q. We know that velocity of transverse wave in a string is tension over linear density, square root of tension over linear density. Then tension of P is greater than tension of Q. Therefore, velocity of transverse wave in string P is greater than velocity of transverse wave in string Q. And according to V equals F lambda, they have given frequency is constant. Therefore, velocity is directly proportional to wavelength. It means when increasing velocity, wavelength also increases. Then we can get velocity of P is greater than velocity of Q. Therefore, wavelength of P is greater than wavelength of Q. Now I will consider fundamental and first overtone for a same string. Shape of fundamental frequency is this one. Shape of first overtone this one. In this diagram, half of wavelength equals to length. In this one, half of wavelength into 2. It means wavelength equals L. Now we can compare. When increasing wavelength, number of loops decreases. Therefore, wavelength of P is greater than wavelength of Q. Number of loops in P should be less than number of loops in Q. It means number of loops. Then we can get A as the correct answer. Number of loops in P is less than number of loops in Q. In answer A. B is incorrect. In B, number of loops in P is greater than number of loops in Q. We can consider C is correct. In C, there is only one loop in P string. There are 3 loops in Q string. Then we can get A and C only. Answer is 3. Two guitar wires A and B identical in all aspects except the diameter of that the diameter of A is twice the diameter of B and are subjected to a same tension. The ratio fundamental frequency produced by A divided by fundamental frequency produced by B. There is the same length for A and B, and they have considered same overtone fundamental. Therefore, wavelength is constant for both strings. We can get this relationship. V equals square root of tension over linear density. tension is constant, therefore velocity of transverse wave inversely proportional to square root of linear density. Linear density means mass per unit length. I will consider unit length 1 meter of a string, and I will consider cross-sectional area A. We can write it pi d squared over 4, pi r squared. R is diameter divided by 2. Then we can write mass per unit length is the mass of this string, 1 meter length. You know that density equals mass divided by volume. Then mass equals density into volume. We can get volume 5 d squared over 4 into 1. Then mass of unit length, mass per unit length, directly proportional to square of diameter. Then we can get V directly inversely proportional to, we can use square of diameter for the linear density, because of linear density is directly proportional to square of diameter. And we have to put square root. We can cancel out square and square root. Then V inversely proportional to diameter. Velocity inversely proportional to diameter. Then we can use V equals F lambda for both situations. V equals F lambda. I will use it for string A. V, we can get lambda is constant, therefore frequency directly proportional to velocity of string, velocity of wave in string. Then we can get velocity of wave inversely proportional to diameter. Now we can get FA, frequency of wave produced in A, inversely proportional to diameter of A, and frequency of wave produced in B, inversely proportional to diameter of B. Now we can divide these two relationships. Then FA or FB equals to 1 over dA divided by 1 over dB, which means multiplied by dB, multiplied by reciprocal. Now they have given diameter of A is twice the diameter of B. Therefore, we can use 2 times dB, 2 times diameter of B for the diameter of A. Then answer should be half. Answer is 2. When a standing wave is set up on a string fixed at both ends, one number of knots is equal to number of antinodes. No, we know that number of knots is always greater than number of antinodes. If we are considering fundamental, it is like this. Antinode means points which are with the maximum displacement. Antinode. These points are nodes. Points which are not moving are nodes. Then second statement, the wavelength of the wave is always equal to the value obtained when the length of a string is divided by an integer. No, we can get for this one lambda 2 equals L. Lambda is 2L. Then we have to multiply length to get the wavelength. Then second one also incorrect. Third one, the frequency of the wave is equal to the value of number of nodes times fundamental frequency. No, we know that for this one, frequency is fundamental frequency. It is 1 times fundamental frequency. One means number of antinodes, not number of nodes. Fourth one, the frequency of the wave is equal to the value of number of antinodes times the fundamental frequency. Yes, it is correct. Number of antinodes 1 into S naught. When considering next situation, first overtone, number of antinodes 2, then frequency is 2 times fundamental frequency. Then fourth one is correct answer. The figure shows the shape of tsunami wave of wavelength lambda, amplitude A, reaching the beach. The speed of wave can be approximately given by V equals root GD, where D is the depth of the sea. When wave reaches the sea, we have to consider lambda, V and A, wavelength, velocity of wave and amplitude. We know that when the wave is moving towards the beach, depth is decreasing. Depth decreasing. Velocity of wave is given as root GD. When decreasing depth, velocity is decreasing. Then velocity decreases. You have to remember it. Then, according to V equals F lambda, we can use V equals F lambda for any type of wave. Frequency is not changing, it is constant. Because of frequency is depending only on the source. It is not depending on moving medium or any other factor. Frequency is depending only on source. When decreasing velocity, wavelength is decreasing. Then velocity wavelength decreases. Now we have to consider the wave shape. In this one, wavelength is a large value. In this one, wavelength is a small value. Now we can get when wavelength is decreasing, the wave is like this. It means there is a high amplitude. Then amplitude increases. Velocity decreases, wavelength decreases, and amplitude increases. Then answer should be 2. There are 4 loops, and when increasing frequency, when the frequency is doubled, it means frequency is 2x. number of loops should be doubled. It means there are 8 loops. Then answer should be 5. When a guitar is played, it will produce, we have to consider wave type in string and wave type in air medium. We know that the wave pattern in the string is not moving after the length of string. Therefore, it is a stationary wave. But for the air medium, the wave is a sound wave. It is moving in the air medium. There is no any limit. It is moving up to the energy loss. Then we can get in the air medium there is a progressive wave. Sound wave is a progressive wave. And in the string there is a transverse vibration. It means wave is moving in this direction and this direction. There is an incident wave and reflected wave. Particles are moving perpendicular to the wave motion. Therefore, it is a transverse wave. But the wave in air medium is longitude. It is vibrating parallel to the moving direction. If the wave is moving to the right hand direction, particles are vibrating parallel to the path of wave motion. Now we can consider given answers. Transverse standing waves on the string and longitude progressive wave in air. Then answer is 4. Two identical strings are separately subjected to a tension T. When plucked at the middle, each string produces wave of frequency F. Now the tension of only one string is reduced to 0.81 T and the strings are plucked at the middle simultaneously. 5 beats can be heard during 1 second. The value of F is, they have given strings are plucked at the middle point. Therefore, it is producing fundamental frequency. Both strings at both situations producing fundamental frequency. In first situation, each string produces wave of frequency F. Initial situation frequency F. If the tension of only one string is reduced, I will consider tension of this one is reduced. We know that V equals tension over linear density square root. When the tension decreases, velocity decreases. Therefore, according to V equals F lambda, when the velocity is decreasing, frequency is decreasing, lambda is constant. For this whole situation, string is vibrated with the fundamental frequency. For all situations, string is vibrated with fundamental frequency, therefore wavelength is constant. Then frequency should be, frequency of this situation should be less than f. And they have given 5 beats are produced. Therefore, frequency of this one should be f minus 5. Frequency is decreasing. 5 beats means frequency difference between these two strings should be 5. Therefore, this one should be f minus 5. F minus 5. Then we can use V equals f lambda for both strings. In first one, we can use V equals f lambda. Velocity is square root of tension over linear density, f lambda. We can use this equation for the first string, and again we can use same equation for this situation. Now tension is 0.81 T over linear density equals frequency is f minus 5. Wavelength is constant, we can use same value lambda. Then we can divide these two equations. We can cancel out T and M and lambda. 1 over square root of 0.18. 1 over square root of this value 0.81 square root should be equal to f over f minus 5. 0.81 means 81 divided by 100. Then we can substitute 81 divided by 100 is 0.81 root equals f divided by f minus 5. Now I will get square root. Square root of 110. Square root of 81 9 equals f over f minus 5. We can simplify this equation. 10f minus 50 equals 9f. 9f. Then f equals 50 Hertz. Then answer is 2. A sonometer wire having mass per unit length 1 gram per meter and tension of 40 Newton is simultaneously sounded with a tuning fork of frequency 320 Hz. While varying its vibration length starting from a small value. In this process, if 5 beats of frequency can be observed on an oscilloscope. The corresponding vibration length in meters of the sonometer wire. 5 beats can be heard. Then frequency should be 325 or 350. It means frequency, fundamental frequency is different between frequencies of wire and tuning fork. They have given beat frequency is 5 and frequency of tuning fork is 320. Then for the given situation, if there are 5 beats we can hear 5 beats. Therefore, frequency of wave in wire should be 315 or 325. Difference is 5. Now I will use V equals S lambda. V is tension over linear density, square root of tension over linear density. We can get S value, frequency of wire for the first situation 315. They have given vibration length is starting from a small value, Therefore, it should be fundamental frequency. Then we can get fundamental frequency means there is only one loop, then lambda over 2 equals to length of the wire. Lambda over 2 equals L, lambda equals 2L, 2 times length. I will substitute 2 times length of the wire. And we can substitute tension, 40 Newton. Linear density, 1 gram per meter, 1 into 10 to the power minus 3 kilogram per meter. 315 into 2S. Then we can find the length in first situation. I will consider it as L1. Square root of this value, 40,000 square root, means 200. Divide by 315 into 2 is the first resonance length. Divide by 2, 100. Divide by 5, 6, 3. Divide by 5, 20. Then we can get 20 over 63 is the corresponding resonance length when frequency is 350. Now I will use same equation. This value is not changing, 200. Divide by, now frequency should be 325 for the new resonance length L2. I have subjected L2. Divide by 2, 1. Divide by 200. Then we can divide by 25. 32 divided by 25, 1. 7 remaining. 75 divided by 25, 3. 4 over 13 is the resonance length in second situation. Then answer should be 4 over 13 and 20 over 63. Third one is the correct answer. Consider the following statements made about a standing wave on a stretched string. Standing wave on a stretched string. Statement A. The energy does not propagate along the string. Yes, it is correct. For a standing wave, energy is not propagating. B. The position of knot does not vary with time. Yes. It is always a constant point, not moving along the string. When considering fundamental, knot is always at 2 ends. Then B is correct. Statement C. Maximum displacement achieved by each particle in the string depends on its position along the string. Yes. Then considering this particle, it is not moving. Maximum displacement is 0. For this particle, maximum displacement is this value. For this particle, maximum displacement is this value. Then maximum displacement of a particle is depending on point of the particle. Then C also correct. All A, B, C are true. Answer is 5. To identical transverse waves of frequency 300 Hz and speed 30 meters per second, traveling in opposite direction along x-axis, superimposed with each other, produces a standing wave. The distance between node and its adjacent antinode D is equal to. Distance between node and adjacent antinode means this length. We have to find half of wavelength. This one is a full wave. We know that there are 2 loops for full wave. Then distance between adjacent node and antinode is the 1/4 of wavelength. Half of loop, it means 1/4 of wavelength. Then we can get V equals f lambda, and we can calculate wavelength. Velocity is given as 30, frequency 300. We have to calculate wavelength. Wavelength is 0.1 meter. It means 10 centimeters. Now we have to find lambda of 4. 1/4 of wavelength. 10 divided by 4. 2.5 centimeters. Then answer is 1. The figure shows composite string made of same material. The cross-sectional area of string B is twice that of string A. The other end of B is attached to a fixed ball. If the both strings are under same tension, which of the following graph best represents the variation of speed of transverse wave generated in string with distance x? We know that velocity of wave, transverse wave, square root of tension over linear density. And we have found linear density is directly proportional to square of diameter. Velocity inversely proportional to tension constant, inversely proportional to square root of square of diameter means diameter. For the string B, cross-sectional area is twice. No, we have to consider cross-sectional area, not diameter. Mass per unit length is I will consider 1 meter length and cross-sectional area A. Then we can write mass is volume A into 1 into density, A rho. And therefore, this one is constant. Mass per unit length is directly proportional to area. Then we can use square root of area. Then considering square root is twice, A is 2 times, velocity should be 1 over root 2 times. 1 over root 2 times. Velocity should be 1 over root 2 times. It means velocity is decreasing, but decreasement is less than half. 1 over root is less than half. 1 over root 2 is less than half. Therefore, there is a decreasement, but decreasement is less than half. Then answer should be 2. So consider the following statements made regarding tsunami waves. A. Wavelength of wave in deep water are lower than that of shallow water. We know that velocity of tsunami wave equals to square root of Gd. G is gravitational acceleration, D is depth. V equals root Gd. In the deep sea, G is a higher value, velocity is a higher value. According to V equals F lambda, we know that F is constant because of it is depending only on source. When increasing velocity, lambda is increasing. Then for the deep water, lambda should be a higher value. Statement A, wavelength of wave in deep water lower than that of shallow water, it is false. Then statement B, speed of waves are higher in deep water than shallow water. It is correct. C, amplitude of wave in deep water are higher than shallow water. We know that when lambda is decreasing at the shallow water, lambda is decreasing. Therefore, amplitude should be a higher value. Now they have given amplitude of wave in deep water a higher value, not it. It is false. Only B is correct. Then answer is 2.